All right, welcome back. Today we're going to be balancing a crankshaft, and it's a Coyote crankshaft. I want to say it's a 2016, 2017, and I might be wrong on that, but it's still a 5-liter Ford. It is coming apart with stock stuff, which is over here on this side, and it's going back together with aftermarket. So we're going away from a cast hyperiotic piston, and we're going to a forged piston. So there's going to be a change there. The next thing that's going to change are the connecting rods, and we see this is a factory rod here, and then this is the aftermarket rod on this side. The other things that'll change about it are going to be the wrist pins. The bearings, they're pretty much going to stay the same, and then we have the piston rings, which will change a little bit. Now, before we actually get into the balancing, I want to talk about what the crankshaft is balanced for. We have a series of pistons and rods that are not only going up and down inside a cylinder, but we have the large end of the connecting rod, this end right here, which is actually rotating around. So they separate the two masses with the terms reciprocating and rotating. And we have some components that are purely reciprocating, and we have some components that are purely rotating, but then there are pieces that are a mix of the two. So it'll be partially rotating and partially reciprocating. So here on the table we can identify the things that are definitely reciprocating only. So something that is only going up and down inside the cylinder. So we can start off with the piston rings. That is definitely just going to be reciprocating up and down inside the cylinder. And then we have the piston. It is only going to be reciprocating up and down inside the cylinder. The wrist pin, and then of course the pin locks. Now on the other end of the spectrum, going from reciprocating to rotating, well, we only have one component that is purely a rotational mass, and that is going to be the rod bearings, because they only ever go around in a circle. They don't reciprocate, only going back and forth in the cylinder. Then the component, because it's a singular component that kind of blends the lines between the two, is going to be the connecting rod. Because the connecting rod is mounted to the crankshaft, but it is also mounted up to the piston. So we can say this connecting rod is really split between those two worlds. This end of the rod, the big end of the rod, is the one that's going to be attached to the crankshaft, and it's going to be operating in that rotating action. But then the other end of the connecting rod, that's got the wrist pin, and the wrist pin is then slid into the piston. This component is only going to be reciprocating, and somewhere in between there's going to be a mixture of the two. So we take into account on balancing crankshafts these components right here. Okay, when they manufacture a crankshaft, they're going to determine the needs of the connecting rod bolts, the piston rings, and the wrist pin. And by using this, they can calculate what the counterweight needs to weigh on the crankshaft. And we'll get to that in a little bit. But these components here are going to determine the size, the shape, and the mass of the counterweights. So if we were to upgrade these components to, say, heavier components, or you could go the other way and maybe put in lighter components, then those counterweights on that crankshaft don't accommodate those components anymore. So if we put in a denser piston, okay, if we put a piston like this one here, which is forged, compared to this one, which is going to be a cast hypothetic piston, this piston, even if it maybe is made with the same volume of material, it's going to weigh more. So the piston's reciprocating mass is now greater. That means that the counterweight is insufficient in size and its own mass. Well, the wrist pins, they can also change, because we have a wrist pin here, the factory wrist pin, which actually has a tapered wall on the inside. So it starts out very thin. So let me grab these calipers, and it starts out at roughly 140 thousandths. And then as I go in further with the calipers, it goes to a largest measurement, the largest wall thickness of almost 200 thousandths of an inch. So the inside of this piston has got a tapered internal diameter, and that's what they mean by tapered pins. The reason they do that is because this wrist pin has really got 3 load-bearing areas, but it's really 2. The center section where the connecting rod goes is only this wide. Okay, so this section right here has to be pretty strong. But then we have these outer sections which are both supported in the piston. So they can thin the walls on the ends here because these sections really take the same force that this one has, but it splits it between this end and this end. That's why tapered wall piston wrist pins are good. You can lighten the weight, which would then be able to reduce the mass of the counterweight, which would overall reduce the mass of the crankshaft, making it easier to spin and more efficient. Now when we go to performance stuff, especially for high horsepower, now if this was a road course engine, and let's say it needed high RPM, we'd want something lighter, we would go back to a tapered pin. But in this one here, we are going for turbocharged application. We're going to triple or quadruple the horsepower of the engine. This wrist pin is thicker on the inside, and it's not going to be tapered. So this one had a greatest thickness of about 200 thousandths. This one has a wall thickness across its whole length of 185 thousandths. Now, it might have a thinner wall through it than this one had in the center, but because this one's thicker all the way through, it will be a stronger pin. It's also made of a better material. This is an OEM where cost is king, where it needs to be a very low cost, still meet tolerances and factory specifications. But this guy right here, cost is not really the biggest issue. It's made of a higher quality material. They make it 185 thousandths thick wall, and it is not tapered. So the pin can get heavier, and that's going to affect the mass of the crankshaft counterweights. So we talked about the pistons, talked about the wrist pins. Now the bearings won't change very much. So these are factory bimetal bearings. So if they go to a tri-metal bearing, there'll be a slight increase in the weight of the bearing, but really just a very minimal increase. So in this application, or in this exercise, I'm actually going to use the same bearings in building the bob weights for each one of these, or comparing the weights between the two. Now piston rings, there can be an increase in weight, but piston rings themselves don't weigh very much, and because it's a reciprocating weight, it's not that big of a deal, so there's not going to be that big of an increase. And then we come down to, probably in this application, the greatest increase in weight. So we have a powdered metal rod here on the right, and then on this side we have a forged billet rod where this guy is much stronger. You can see down the length of the beam, the one here on this side has got a lot thicker beam, or a lot wider beam, compared to the original factory one. And then on the big end of the connecting rod, we have our cross section where the bolt goes through. Where on this one, the factory rod, we have a cross section measurement of about 0.520. We go over to this aftermarket rod, and now we have a cross section thickness of 0.620. So there's 100 thousandths of an inch thickness increase from this rod to this rod. That means there's more material there. Okay. The other thing about it are the bolts. So these bolts are going to be probably an 8mm by 125 or a 1.0 bolt. These are going to be, let me see, it's a 3/8 or a 7/16 bolt. I haven't had them out yet, but either way, the bolt is going to increase because this is going from roughly a .315 up to a 0.375 of an inch bolt. So the bolt is going to increase in diameter. Now, they can offset that because they can install a shorter bolt in this connecting rod if they determine it's necessary. Now, we go to the other end of these connecting rods. On the small end of the rods, we can see that there's actually more material right through here. This is the top of the pin, and this material is important for RPM. So we have on this one a 215 thousandths, and then we go over to the powder metal rod. This one is 195 thousandths. So we have an increase of 20 thousandths of an inch from here over to here. So this rod is definitely going to be heavier, and that means we'll have to change the weight of the counterweights on the crankshaft. All right, so we're going to do some comparisons between the factory stuff and the aftermarket stuff. But first I want you to understand the scale of what we're doing, kind of the resolution of this weight scale here. Now, this is a single dollar bill, and I'm going to place this on the scale, and we're going to see about how much we got. See, we're zeroed out. I drop that down on there, and we get about 1 gram. So when we see a difference between two components of, 0.1 grams, that's almost nothing, okay? 0.1 gram would be to take this dollar bill and cut 1/10 of it off, and then that would be 0.1 gram. Now, I'm not saying that we don't balance things to that level, but that's what's happening when we're balancing something, is that we're trying to get down to 0.1 grams to figure out or try and balance something properly. So the first thing I want to try is the wrist pin. So we see this first wrist pin. This is the factory one, comes out to 120, and that's a pretty heavy pin. So 120 grams for the wrist pin. And then we have our aftermarket. Okay, the aftermarket comes out to 112.8. So we actually have a decrease in weight. So let's just double check, go back to 0. This one comes into 120. And then this aftermarket one comes into 112.9. So we can say 113 grams. So we actually save weight. Now the weight savings comes in primarily in the length difference. We can see if I square the ends of the pins up, we can see that the other end of those pins are not the same length. So this one is a longer pin, even though it's got a taper wall on it. Okay, the next thing I want to take a look at are the wrist pin retaining clips. These aren't much, but let's see. They'll come out to 1.9. And that's the factory clips. And then we got the aftermarket ones. The aftermarket comes out to 1.8. Double check. 1.9 and 1.8. So we have a 1/10 of a gram difference between the factory and the aftermarket. So far, we're actually less by about 8 grams. The next thing I want to do are the piston rings. Now, these are the factory piston rings, and our numbers might be skewed just in a very small amount because these rings are actually dirty. I did wipe them off, but any of the carbon or the oil that's in the ring, especially with this expander ring, will skew the numbers, but only a very small amount. So the factory rings come out to 24.1. There we go. Make sure it goes back to 0. The aftermarket rings come out to 23.7. So We're getting lighter. So it looks like we have about, say, 7, yeah, still about 8 grams difference between one rotating assembly to the next. Now the bearings, these, I'm just going to go ahead and do this so we can get the numbers. We're going to see what the bearings give us. Keep them from moving there. Comes up to 48.5. Okay. And we'll be using similar bearings on the new one. So same thing about the piston rings. I did wipe off and clean off the large pieces of carbon, but there's still some stuff deposited down inside the piston, but it's really not that big of a deal because it's so small, such a small amount. Now this piston looks like it weighs 356.9, 356.8. So 356.8 is the stabilized number. All right, here's the aftermarket forged piston. All right, let's see. This one comes in at 360.6. So we've had an increase due to or a decrease in weight due to the pin by about 8 grams. And then we have an increase in weight due to the piston by about 4 grams. So the piston is 4 grams heavier. But remember, that's $4 bills worth of weight. When they design these pistons, they can design them in such a fashion that they can be very cognizant of the weight of the piston. By using these cavities through here, and to restore strength, they can put strutting back in there. They can also change the width of the skirts, because if we look how wide the factory skirt is compared to this aftermarket skirt, you know, they can decrease the width of it if they then determine that that would be a sufficient width on it. Now when it comes to the connecting rods, we're just going to do overall weight right now. So here's the factory connecting rod. Overall weight of this rod looks like it comes in at 615.5. 615.5. Yep. So pretty heavy factory rod for a modern engine. And now we're going to put on this one. What's it going to be? 700? 600? Let's see what it goes to. 666.7. So we have an increase of about 50 grams from the factory rod over to this aftermarket rod. So that means that our factory crankshaft with its original counterweight is going to be insufficient. And we'll actually have to add weight to that. Now the other thing that I want to talk about before we move on is what weights are considered. Now, like I've said, the components that we're going to have to consider are the piston, the connecting rod, the piston rings, the wrist pin, the clips, and the bearings. All these pieces right here are what we're going to use to consider, or to try and calculate what the mass is that we're going to use to mimic them when we're balancing the crankshaft. But there's still some things, because remember we talked about reciprocating and rotating. Because the crankshaft is only rotating, it's going to be more greatly affected by components that are rotating. So when we take this connecting rod, we're going to measure it in 2 different ways. We're going to measure its overall weight, and then we're going to measure just the big end using an apparatus to hold it up onto the scale. Now, the component of the rotating piece, we're going to take 100% of that weight and apply that to the calculation. The bearings, 100% of their weight are going to go into that calculation. Everything else, all these other pieces on this side right here, they're all reciprocating. And because they're reciprocating, we're only going to take 50%, that's 50% of their weight into the calculation. So we have lost weight on this side over here, but because we're only taking half of that weight loss really isn't that big of an impact on what the counterweight is going to be changed by. The connecting rod is going to be the biggest thing that's going to affect our counterweight modification when we go to balancing this thing. Okay? All right, let me set up, and we're actually going to measure out the components again for the new bob weight assembly. I'm going to have a bob weight, and then we're going to build that bob weight for our new stuff here. Okay? So I'll be back. All right, so we're back, and what we're going to do is actually measure the pieces out for the bob weight that we need to build on this crankshaft rebalancing. So let's just go ahead and do these over again. We have our new wrist pin, our new clips, our bearings, our piston rings, the connecting rod, and looks like we're all ready to go. So the first piece, let's go ahead and do the piston. Let me verify the numbers. Okay. Piston comes out to 360.6. That's what we got before. Okay. The next piece are going to be the piston rings. Comes up to 23.7. That's what we got before. Then our wrist pin should be 112.9. Our retaining clips, .7. It's off by 1/10 of a gram from last time. That's right there. So we're just going to go ahead at 1.7. That's our clips. Okay, so those are the components that are all reciprocating. Now we're going to do our bearings for rotating. Comes out to 48.5. And then our connecting rod. Our first measurement of the connecting rod is again going to be the overall weight, the whole weight of the rod. Comes up to 666.7. 666.7. Now the next component, I want to be able to measure just the big end of the rod. Now I could hold it like this, but this isn't very repeatable because one, if I hold it like this, I'm going to get one weight, or if I hold it like this, I'm going to get a different weight. Because if we look at the force, as I stand this up, more of this material starts to go over this point, and I start to weigh more and more of the rod. I'm trying to measure just the big end of the rod. So to do this, I've got this component here, which has got a pendulum that has bearings here in this pivot, and it also has bearings up here, and that's where our rod's going to sit. And then we have the other component of this assembly, which is going to support the small end of the rod. Now I need to take a little bit of time to set this up. Now I do need to re-zero this because I want this weight canceled out. So I tear it. I'm going to put this rod on here, put it out here, and I'm looking to see how it's sitting. I need this rod to go straight off of my pendulum here. And I want to make sure when I pick up this end of the rod, if we watch this bar, I don't want it to swing that way or this way. I want it to pretty much stay right where it's at. So you saw it went over to this side here, which would be to the right. So I'm going to move my stand out just a little bit. I went just a little bit too far. And I can be very, very specific on positioning and how everything's held. Now, notice our rod is pretty level, so I'm good with that. I could move this chain up and down on this side, but I think we're good. Okay. All right, so with it the way it is, it comes out to 478. And that's 0.0. Now that we've got it set up, let's go ahead and do a comparison to the factory rod. 478 grams on the aftermarket rod. And now we're going to the factory rod. And we're at 443. So that means just on the big end of the connecting rod, we have an increase of about 35 grams. And that all comes down to what we're going to have to do on the counterweights. Okay? Next thing I'm going to do is going to bring a crankshaft up here and talk about the counterweights and what all this is going to do and how it's affecting the counterweights. And we're about to build our bob weights, but before we get into that, I wanted to show you something. Because this is a V8 engine, it has 4 rod journals. And each one of those rod journals is going to get 1 bob weight. So that means that we're going to have 4 bob weights total. If this were a V6, which would have a splayed rod journal, then we would more than likely need to have 6 bob weights. So we can see how big this guy is. I mean, this is going to be, 1,700 grams, because this is going to mimic the weight of 2 rods and 2 pistons, 2 sets of rings and all that stuff. But when we come to a V6 engine, V6 engines have 6 rod journals because they're usually going to be a splayed rod journal to keep the firing order even. So we can see that this bob weight here, this is for V6, is considerably smaller. And we see its overall dimensions is quite a bit less because this bob weight is only for 1 piston and rod assembly. So that's a V6 bob weight. So if you ever ask a machine shop to balance up a crankshaft for you and it's a V6, it will probably cost more than a V8 crankshaft bob weight or a balance job. All right, so we need to zero out our scale. Now we're going to be shooting for 872.8. So let's build us a bob weight. Now the dimension that we're going for, or the weight that we're going for, is 872.8. So I need to put the nuts on here that are going to go onto this half bob weight. And we're going to set the bob weight down so it don't fall. And we want to get to 872.8. So it looks like we're at 887. So I'm going to take off one of these guys. Let's see where we're at. We're at 868.6. Let's see what one of these large, and these are actually thinner, is going to take us up to 873.1. So we've overshot our weight by 0.3 of a gram. So let's try and make this the best we can. Now we're going to step down to these little blue ones, and these are usually coming out to 1 gram a piece. And we're slowly going to step up to 872.8. So there we are, we're at 872.4. And let's see what this thin black one does, and that should take us up to 872.9. So we've overshot it by 1/10 of a gram. I think that'll be good enough, because remember, that's just a sliver of a dollar bill I'm going to slide these washers on, and we're going to see, oh, wrong one. I'm going to tighten it back down. There we go. We're going to tighten it, set it back on the scale, and make sure we have the numbers that we expected. 872.8. We have 872.9. So we're going to set this one to the side, and we're going to do the next one. Okay. All right, so we're going to put the bob weight half on, and then we're going to put the nuts on. We're at 849.7. Let's try one washer. 868.1.2. So we're going to step up one at a time. 870.1. We want 872.8. All right, looking good. So we can overshoot it by 0.2, or we can undershoot it by about 0.3. I think because we overshot this one by a small amount, let's go ahead and keep it undershot by about 0.2, 2 or 0.3. Same thing here. We're going to put all the washers that we use to weigh or use to build the weight, install the nut. This is really just a sanity check. We're going to make sure we have that 872.5. Cool. Now, the last step in our building of the bob weight is to put the two bob weights together, put the two locking nuts on. These are tight, and we're going to measure the weight, and these to come out to 1,745.6. 1,745.5, off by 1/10 of a gram. So while this engine is spinning at 8,000 RPM, this crank is going to possibly be out of balance by 1/10 of a dollar bill. Sad, I know. All right, so what I'm going to do is go ahead and build out the rest of these off camera, and I'm going to meet you over at the crankshaft balancer. See you then.